So my name is Pillonnet. I'm from CLET from Grenoble. I'm a research scientist in power management context. So I will present to you some trends and issues concerning the power management in IoT context. So this nice picture is just to say it's a new deal for power community because there are a lot of things to do for IoT, and it's a big challenge for us because there are new constraints. So first, I will just describe the title. So just first part is power management. So don't forget, I will say, because we did a lot of work to design very good IPs and with nice performance. And sometimes we forget to move from your clean power supply to a battery. And if you put battery instead of your clean power supply from your lab, it could be a nightmare because you lose some performance. So you lose maybe 20 dBs on your factor of merits. And if you put IP together, and with the same power raise, it's also reduce the performance. So take care of that because it's very challenging for IoT. And at the end of the road, for mobile phone, for example, it's not IoT, but it's for mobile phone. For a board, it's something like 20% or 30% of the board is dedicated for power management units, so power supply, power management, and other external components. And as Intel say, it could be half of your overall loss in your systems. So take care because you can do a best job for designing your IPs, but you have to take care of the loss due to the voltage regulators or IC to DC converters. So the second part of my title is IoT. So everybody know this word, but nobody know exactly what that means. So maybe for me it's the same things. Just to say, if you discuss with computer science people, they say, okay, for me it's big data. And for me, from my community, it's more voltage regulators, low power voltage regulators. So there are a lot of buzz, but anyway, this is a technical challenge, so I don't know if it's a true business, but anyway, we'll go to try to find solutions. So here, the focus of the presentation is more for local sensings and to supply this kind of nodes. So there are a lot of devices spread anywhere. So we have to take care of the solutions because if you find a good solution but we cannot spread massively, it's not a good solution. So what is the question of this talk is just to say, how do you supply power to numerous devices to allow autonomous operation in the IoT context? So maybe you already see the movie from Walt Disney. You have a nice robot called Baymax, and in some time there is no battery inside, and he cannot help the people around him. And I think Walt Disney has a good vision of IoT, because if you design a good robot, but if you don't think about the autonomous operation, it's not a good thing. So first, for power management community, it's new, because IoT, you cannot plug your device in a classical electrical networks. So you need to be wireless somewhere. And you have to be compact, you have to be long-term operation, so it's not like for mobile. You don't just need 1 day of operation, it's 10 years or 1 year. And you have to be safe, so you cannot spread a chemical battery everywhere. It's not possible. Not because you are green, you take care of a green party, but you have some regulations just behind these constraints. So I like this picture because for IoT, it's like for estates. So you have to generate power somewhere, you have to store, you have to transmit this power, and you have to feed the home. So here, the home is the IoT nodes. So the key questions is how to generate, store, and distribute the power. First, to know how many power you need to generate, you have to know the home consumption. So fortunately, the IoT nodes is, like I would say, basics, simple, and electric engineer do a good job to reduce the power consumption of these nodes. And it's something like when you do an operation, it means 1 millijoule of energy. So 1 millijoule is very small. It's like when you move an apple up just for 1 millimeter. So it's not too much. So just to switch on, send something, just send by wireless transmission channels. So you can say, okay, there is no problem with IoT energy challenge. But there is a problem. It's not the end of my talk. It's to say, okay, it is an energy challenge. Not yet. If you assume 1 milliwatts average power consumption on 10 years of operation, so it's not very large. And if you multiply to calculate the energy, so the power multiplied by the time, it's something like 300 kilojoules. So you can say, oh, it's large, but it's equivalent to when you are in the car and you are at something like 30 kilometers and you stop your car. So this energy, it's the equivalent energy to power one IoT node for 10 years operations. So it's something like 7 grams of gasoline. So it's not enough. It's not too much. And if you multiply by the expected IoT node, it's something like less than 1% of the electricity produced in France in average. So it's not an energy challenge for considering this kind of things. But the problem is the chemical battery. The problem comes from chemical colleagues, not from electrical part. It's if you want to store 10 years of operation to supply your IoT nodes, it's equivalent to 1 liter of battery. So 1 liter of battery, you cannot spread 26 billion of IoT nodes in the environment like that. So if you are not agree, just take an example of actual battery in mobile phone, and you can calculate just with the data on the battery, and you can say it's true, you need 1 liter of chemical battery. Why? Because if you see the graph, it's the energy density per volumes. So here it's the battery, chemical battery. Here it's the gasoline. So gasoline, it's very good to store energy. Here it's corn. Here it's coal. So you see that it's very, very bad energy storage for chemical battery. So what is the alternative solution? There is high density storage. So it means you take over materials to store your energy, or you harvest your energy from your environment. So each solution, or something like hybrid solution between them. And if you take the actual literature concerning the chemical battery, and if you take the best number concerning the energy density, you can see that it's something like 4 megajoules per liters. So for our example, it means you need half of a glass of battery in the base case to store your overall energy for 10 years of operations. So maybe it could be enough for some application, but sometimes it's not possible. So there is some alternative solution to store the energy, like a gasoline. But the problem with gasoline is you have to transduce this energy to electrical energy. So you need like micro motors if you want to be integrated. So there are nice work from Berkeley, like in these fields. Many people try to store energy inside hydrogen because it's very high density materials. And also like a biofuel cell. So I think it's a nice work from people in nature in the last year to see that you can store a lot of energy inside like tissue, human tissue, skin. For energy, concerning energy harvesting, there are a lot of things to do also. Because it's free, so it's nice for businessmen because it's like El Dorado. It's a Far West. And there are a lot of solutions. So many people know solar panels or something like mechanical vibration. But don't forget like thermal gradients. It's nice to use, or carbonate substrate, so you can scavenge the energy from the bio substrates, or nuclear radiation in some environments. It works also. The problem is there are a lot of jobs for system level designer because in one system there is no universal answer. It's if you are close to the motors, maybe it's more easy to harvest vibration, but sometimes it's not true. So we have to take care of your environment. So there is no, it's not like chemical battery, you just put your chemical battery and that's all. Here it's not the same challenge. And if you have not enough energy in your environment, you can put more. So it's like active energy harvesting, like you put some wireless power, and you transmit by some capacitive or inductive coupling. So it's nice, but be careful of the overall efficiency because you have to send a lot of power to grab very little. And if you grab from your energy from your environment. Take care of other device close to here, because there are a lot of crosstalk sometimes. If you have a big antenna, sometimes if you want to have your wireless Wi-Fi in your computer, and if you have IoT nodes somewhere, it could be shut down your internet connection, so take care of that. It could be crazy if everybody grab the energy from the environment. When you design IoT nodes, you say, okay, I have to be compact. So how much? It's hard to answer this question, but you can, in the power community, we have factor of merit like over communities, and it's called the energy density. So it's a cube centimeters. So to give a number, it's something like 100 macrowatts per cube centimeters or square centimeters. And you see also some example here. So sometimes it could be big, sometimes it could be small, depending on your environment. Just to have a reference, for 1 cube centimeters of battery, you can operate something like 6 months. And for the same volume of harvester, you can be like quasi-autonomous systems. So it depends on your design. If you want to have more than one year of operation, you have to think about the energy harvesting solutions. But if you think of energy harvesting solution, you need to store your energy somewhere, because it's not enough to supply directly your nodes. So you have to grab your energy, buffering, and after discharge this buffer. Fortunately, the supercapacitor has a very good energy density, large enough to be that the volume of this battery is negligible compared to the harvester volumes. So now we generate from your power plant, so here it's a harvester. You have to step up this voltage because it's not directly, you cannot directly power your homes, or you cannot directly store this energy. So the problem is, depending of your harvester, you have some AC source or DC source. For example, solar, it's a DC source, but vibration, it's AC variations. And also, like the environments have some fluctuation, you have to be to adapt your electrical interface to these variations. So for example, if you take thermal gradients, so it's a DC voltage with output impedance, and here your interface is something like a small signal models here, so it's DC-DC converters, and the input impedance need to be equal to the output impedance of your harvester, and these models, this small signals model of your harvester will change because we need to be adaptable, because maybe the thermal gradient could be changed. So you have to have some MPPT, so max power point tracking system, to be adaptable of your system's harvester. The problem is each harvester has different models. So if you have vibration, it's more AC voltage source. For solar panel, it's more DC current source. So the MPPT, so the max power point, is not at the same point. Okay, and also the voltage generated by, for example, a vibration harvester, it's very high compared to the CMOS technology, the voltage stress of the advanced CMOS technology. So you have to have some passive components or external components to interface high voltage to low voltage device. So the electrical engineer say, okay, there are a lot of harvesters, so it's not a good business for them. So they say, okay, I will design a new universal interface. So I'm not sure it's a myth or reality, but you can find in some company like TI, ST, or other company like Analog Devices. And it's quite nice because you have a good extraction efficiency, like 70% of efficiency when you have 10 microwatts harvest power. So you can plug many sources like photovoltaic, thermal, piezoelectrics. So it's nice to know that it already exists in the market. After that, you have to store your energy. So it's like a battery charger for your car. You have to take care of your profile. And because if it's a supercapacitor, it's not too difficult, but if you have a chemical battery, you have to take care of that because you need large lifetime for your battery and you cycle many times your battery, so it's something to take care. The other thing is to distribute your power when you have already storage. Here the storage has a large voltage because if you want to store with a high density, energy density, you have to store at high voltage. It's true for a supercapacitor, for example. And you need a step-up DC-DC converter, step-down DC-DC converters to supply many power domains. So it could be very different from processor, memory, or RF amplifiers. So you need multiple step-down converters. So for example, I just take an example. So if your IoT node is something like 1 microwatts average power consumption, and if you have a 1% of duty cycle, it means that your IC consumes something like 100 microwatts during 1% of the time. So if you would like 90% of efficiency, it means for 1% of your time, the loss could be less than 10 microwatts, so it's the question mode. And for the rest of the time, you need something like 0.1 microwatts. So it's very, very little. It's very small. So you have to take care because in the market, if you put like a converter, it cannot have this kind of performance. Maybe the best solution is to put a wire instead of a DC-DC converter because it consumes a lot to have like a DC-DC converters in some applications. There are two main families to step down DC-DC voltage. It's a linear, so linear regulators. It's nice because you can achieve low quiescent current, but you have low power efficiency when you have a large voltage ratio. Like the efficiency is something like the ratio between the output voltage and the input voltage. So as I mentioned before, if you have a large voltage from your storage and you have low voltage, you cannot use this kind of regulators. The overall solution is to use something like switching regulators. So you have switching cells on inductors, capacitors, or hybrid solution to convert DC-DC to DC-DC. So first of things, it's a linear DC-DC. So you have to looking for quiescent current. For example, here I take an existing circuit in the market. So the quiescent current is something like not too bad, and also the idle current is not too bad also. You need large capacitor, so it's also a problem of volumes. I think I have not too much time, so I will skip it. So take care of, because when you have some power management, you need a lot of passive components. So for example, for a mobile platform, it's something like you need something 1 decade more passive component than active component. So take care. Just to finish, just to conclude, it's to show one circuit in the market that generates, store, and convert, just to see a practical example. So it's from TI. I don't work for TI, but it's just one example. Here you have a solar cell here, so it's your power plant. You have a boost converter here to step up your voltage to like a storage. So it's a supercapacitor here. And if you have enough energy, you can step down by a buck converter here. So you see the inductor here to your home, so it's your systems. And there are some supervisor here, so MPPT, like cold starts, and some power management here. So it's nice. It's nice circuit, but it's not universal, as they mentioned in the website. So to conclude, it's just to say we will see many unlocked problem in the literature. So, for example, for power plant, it's the volume of the harvester. It could be a bottleneck. You have to be adaptable circuit to extract the maximum energy from your harvester. You need high voltage gain to store your energy inside high energy density components. And you need like a DC-DC converters, a lot of DC-DC converters to provide low power ICs. So there is no universal solution, but there are a lot of jobs for engineers in this field. So at the end.